The 1989 AB question 2 reads as, let R be the region in quarter 1 enclosed by the graph of y equals the square root of 6x plus 4, y equals 2x, and the y-axis. Part A wants you to find the area of R. To do this, you set the area equal to the integral from 0 to 2 of the square root of 6x plus 4 minus 2x dx, or the integral from 0 to 2 of 6x plus 4 to the 1 half minus 2x dx. Both of these integrate into 1 over 6 times 2/3 times 6x plus 4 to the 3 halves minus x squared from 0 to 2. That turns into 64 over 9 minus 4 minus 8 over 9, which equals to 20 over 9. Part B requires you to set up but not integrate an expression in terms of a single variable for the volume of the solid R rotated on the x-axis. The first way to do this is to set the volume equal to pi times the integral from 0 to 2 of 6x plus 4 minus 4x squared dx. Way 2 is to set the volume equal to pi times the integral from 0 to 2 of 6x plus 4 dx minus 32 pi over 3. Part C is very similar to Part B, but only across the y-axis instead. The first way is to set the volume equal to 2 pi times the integral from 0 to 2 of x times the square root of 6x plus 4 minus 2x dx. The second way is to set the volume equal to pi times the integral of 0 to 4 times y over 2 squared dy minus pi times the integral of 0 to 4 times y squared minus 4 over 6 squared dy. The 1989 BC question 2 states, let R be the region enclosed by y equals x squared over x squared plus 1, the line x equal 1, and the x-axis. Part A asks you to find the area of R. The area is equal to the integral from 0 to 1 of x squared over x squared plus 1 dx. This equals the integral from 0 to 1 of 1 minus 1 over x squared plus 1 dx, which equals x minus arctangent from 0 to 1, which equals 1 minus pi over 4. Part B asks us to find the volume of R about the y-axis. The first way to do this is to set the volume equal to 2 pi times the integral from 0 to 1 of x times x squared over x squared plus 1 dx. This equals 2 pi times the integral from 0 to 1 of x minus x over x squared plus 1 dx. That equals 2 pi times x squared over 2 minus 1 half ln absolute value of x squared plus 1 from 0 to 1. And that equals pi times 1 minus ln 2. The second way is that the volume equal to pi times the integral from 0 to 1 half of 1 minus y over 1 minus y dy. That equals pi times 2y plus ln of the absolute value of y minus 1 from 0 to 1 half, and that equals pi times 1 minus ln 2.
Hello viewers, and welcome to Math with Morse. We're looking at the 1994 AB question 1 free response. Number 1 says, let f be the function given by f of x equals 3x to the 4th power plus x cubed minus 21x squared. A wants us to write an equation of the line tangent to the graph of f at the point 2, negative 28. So what you would do, you take y minus the y value given equals the slope, which is m, times x minus the x value given, where m is the slope at f of 2. So to find that, you take the derivative of f, giving you this equation, then you plug in 2, which gives you 24. So your final equation would be y plus 28 equals 24 times x minus 2, or y equals 24x minus 76. Part B wants us to find the absolute minimum value of f. To do this, we need to find the critical points of the graph of f. To do this, we take the first derivative of f and set it equal to 0. Now, every point where it equals 0, we have to test where the slope is increasing and decreasing. So once you find your values where the slope is equal to 0, which would be at x equals 0, 7/4, and -2. So put that on your number line. This would be the graph of f down here. So the slope is going from decreasing to increasing to decreasing to increasing. Now for minimum value, you would do decreasing to increasing. So that's at -2 and 7/4. So you would have to find which one has the lower point. So you plug in -2 and 7/4 into f to find your y values. And we see here that f of -2 has a lower value. So f has an absolute minimum value of -44. Part C wants us to find the x-coordinate of each point of inflection on the graph of f. To do this, we take our second derivative, which is 36x squared plus xx minus 42. Then we set that equal to 0, and each point would give us our inflection points. So whenever we set that equal to 0, we get x equals -7/6 and 1. And that's our answer. We are now looking at the 1993 BC question 2 problem. The position of the particle at any time t is greater than or equal to 0 is given by x of t equals t squared minus 3, and y of t equals 2/3 t cubed. Part A wants us to find the magnitude of the velocity vector at t equals 5. For now, we're not going to look at the t equals 5. So we're given the x and the y. Now we have to find the dx dt and dy dt. So you get 2t and 2t squared. Then you plug it into the standard form of equation to find the magnitude of the velocity vector. So you plug in your 2t and your 2t squared where appropriate, and you end up with 2t square root of 1 plus t squared. Then you plug in your 5. This is where it comes in. You get 10 square roots of 26. Part B wants us to find the total distance traveled by the particle from t equals 0 to t equals 5. The standard form for the total distance traveled is this formula right here, from 0 to 5, given here. Now, since we have the dx dt and the dy dt, because we solved them in part A, you just plug them in straight there. Then you take your integral, you get 2/3 times 1 plus t squared to the 3/2 power from 0 to 5. You would get s equals 2/3 times 26 to 3/2 power minus 1. Part C wants us to find dy dx as a function of x. To do this, in a parametric equation, when given x of t and y of t, you have to take dy dx equals dy dt over dx dt. Since we use dy dt and dx dt in the first two parts, we already know what they are, so we just put 2t squared being dy dt over 2t being dx dt. This gives us t, which equals x plus 3. So your dy dx would equal square root of x plus 3.